Welcome to Timeless Tales. Today, we're diving into the extraordinary life and monumental contributions of Stephen Hawking, one of the most brilliant minds in the history of science. From his groundbreaking work on black holes to his efforts in making complex scientific theories accessible to the general public, Stephen Hawking's legacy continues to inspire and educate us. So, sit back, relax, and join me on this journey as we explore the remarkable achievements of this scientific icon. Let's start by visualizing the timeline of the universe. This illustration depicts the journey from the Big Bang to the present day, spanning approximately 13.8 billion years. The Big Bang marks the beginning, a massive explosion that gave birth to all matter and energy. As the universe expanded and cooled, the first atoms formed, leading to the creation of stars, galaxies, and eventually, our solar system. Stephen Hawking's theories have provided critical insights into several key stages of this timeline, particularly in understanding the behavior of black holes and the conditions of the early universe. In this video, we'll delve into one of the most ambitious goals in modern physics, the theory of everything, or TOE. The TOE aims to unify all fundamental forces of the universe into a single, all-encompassing theoretical framework. This quest has driven physicists for decades, seeking to reconcile the four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Stephen Hawking dedicated much of his career to advancing this understanding, integrating aspects of quantum mechanics and general relativity. His work has brought us closer to understanding the underlying principles that govern the cosmos. To fully grasp the concept of the theory of everything, it's essential to understand the four fundamental forces that govern the universe. These forces are gravity, which governs the attraction between masses; electromagnetism, responsible for electric and magnetic interactions; the weak nuclear force, which is involved in radioactive decay; and the strong nuclear force, which holds atomic nuclei together. Hawking's work often intersected with these forces, particularly through his efforts to unify them under a single theoretical framework. His contributions have been pivotal in advancing our understanding of how these forces interact on both cosmic and quantum scales. Stephen Hawking's most significant contributions lie at the intersection of quantum mechanics and general relativity, two of the most important theories in physics. Quantum mechanics explains the behavior of particles at the smallest scales, while general relativity describes the gravitational forces acting on massive objects. These two theories often seem incompatible, but Hawking's work on black holes has provided critical insights into how they might be unified. By proposing the existence of Hawking radiation, he showed that black holes could emit particles, a phenomenon that integrates principles from both quantum mechanics and general relativity. Stephen Hawking's work was built upon the foundations laid by other giants in the field of physics. Let's briefly introduce some of these key figures. Albert Einstein, whose theory of general relativity revolutionized our understanding of space and time; Niels Bohr, a pioneer of quantum theory; Werner Heisenberg, known for the uncertainty principle; Max Planck, the father of quantum theory; Erwin Schrödinger, famous for his contributions to quantum mechanics and his thought experiment Schrödinger's cat; and Richard Feynman, who developed the path integral formulation of quantum mechanics. Hawking's work was deeply influenced by these trailblazers, and he often built upon their groundbreaking discoveries. Stephen Hawking was born on January 8, 1942, in Oxford, England, exactly 300 years after the death of Galileo Galilei. His early years were marked by a keen interest in science and mathematics. In 1959, he began his degree at Oxford University at the age of 17, studying physics. Despite finding the academic environment somewhat unstimulating, his curiosity and determination led him to pursue a doctorate at Cambridge in 1962. These early academic experiences were the first steps in a journey that would lead to some of the most profound discoveries in modern physics. In 1963, while still a doctoral student at Cambridge, Stephen Hawking was diagnosed with a slow-progressing form of amyotrophic lateral sclerosis, ALS, a motor neuron disease commonly known as Lou Gehrig's disease in the United States. This diagnosis was a significant challenge, but Hawking's determination and passion for science never waned. He completed his thesis, Singularities, and the Geometry of Space-Time in 1966, which provided important insights into the nature of the universe's origins and the behavior of black holes. This thesis marked the beginning of his long and illustrious career in theoretical physics, showcasing his resilience and brilliance. One of Hawking's most significant contributions to theoretical physics came in 1970 when he proposed the second law of black hole thermodynamics. This law states that the total event horizon area of a black hole can never decrease. This was a groundbreaking concept because it linked the physical properties of black holes to thermodynamic principles, suggesting that black holes have entropy. This insight paved the way for further research into the nature of black holes and their interactions with the rest of the universe, solidifying Hawking's reputation as a leading theoretical physicist. In 1974, Stephen Hawking proposed a theory that would revolutionize our understanding of black holes. He suggested that black holes are not completely black but can emit radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, implies that black holes can lose mass and eventually evaporate over time. This discovery was monumental because it bridged the gap between quantum mechanics and general relativity, two fields that previously seemed incompatible. Hawking radiation has profound implications for our understanding of the universe, particularly in the context of black hole thermodynamics and quantum gravity. Stephen Hawking's contributions to science earned him numerous accolades and honors throughout his life. In 1982, he was appointed Commander of the Order of the British Empire, CBE, for his services to science. His book A Brief History of Time, published in 1988, became an international bestseller, bringing complex scientific concepts to a broad audience and solidifying his status as a public intellectual. In 2002, he was named number 25 on the BBC's list of the 100 Greatest Britons, highlighting his impact on both science and popular culture. Despite his physical limitations, Stephen Hawking continued to contribute to science and education throughout his life. He co-authored a series of children's books with his daughter Lucy, aiming to inspire young readers to explore the wonders of the universe. In 2014, his life was depicted in the biographical film The Theory of Everything, which highlighted his personal and professional struggles and triumphs. Hawking passed away on March 14, 2018, at the age of 76. His legacy lives on through his numerous scientific contributions and his inspirational life story, which continues to motivate and encourage people around the world. Stephen Hawking's black hole theory posits that black holes slowly disappear over time. Traditionally, black holes are seen as cosmic vacuums, pulling in everything, including light. However, Hawking's theory introduces the concept of black holes leaking energy, known as Hawking radiation. Over time, Hawking radiation causes black holes to shrink and eventually vanish. To illustrate, imagine a balloon with a tiny hole. The air inside the balloon will slowly escape, causing the balloon to shrink and disappear. Similarly, Hawking radiation acts like the tiny hole, causing black holes to gradually lose energy and disappear. Hawking's contributions to black hole physics are groundbreaking. He provided profound insights into the nature of these enigmatic objects, including the concept of Hawking radiation, which suggests that black holes can emit particles and lose mass over time. His work also delved into the implications of black hole thermodynamics, proposing that black holes have entropy and adhere to thermodynamic laws. These discoveries have significantly advanced our understanding of black holes, influencing how we study these intriguing objects and their role in the universe. The quest for the theory of everything is one of the most ambitious goals in physics. It aims to unify all physical theories into a single, coherent framework that can explain all fundamental forces and particles. Stephen Hawking's work has been instrumental in this quest, particularly through his efforts to reconcile quantum mechanics and general relativity. By proposing the existence of Hawking radiation and exploring the thermodynamic properties of black holes, Hawking has provided crucial insights that bring us closer to achieving this ultimate goal in theoretical physics. One of Stephen Hawking's most significant contributions outside of his scientific research was his ability to popularize science. His book A Brief History of Time brought complex concepts to the general public in an accessible and engaging way. Hawking's charisma and wit shone through in his public lectures and appearances, inspiring countless individuals to take an interest in science and the mysteries of the universe. His ability to communicate complex ideas in a relatable manner has left a lasting impact on science communication and education. In 2018, Stephen Hawking's ashes were interred at Westminster Abbey, placing him among the greatest scientific minds in history, such as Sir Isaac Newton and Charles Darwin. His tombstone bears a profound and poetic inscription, reflecting both his life's work and his legacy. The inscription reads, "Here lies what was mortal of Stephen Hawking 1942 to 2018. This simple yet powerful statement encapsulates the essence of his journey, highlighting the transient nature of physical existence while hinting at the immortality of his contributions to science. Beneath his name is an equation, symbolizing his most renowned discovery, Hawking radiation. This equation is not just a scientific formula but a representation of his relentless pursuit of knowledge and his ability to bridge the gap between complex scientific theories. The inclusion of this equation on his tombstone serves as a lasting reminder of his impact on our understanding of the universe and his role in reshaping modern physics. At the memorial service held in Westminster Abbey, renowned actor Benedict Cumberbatch, who portrayed Stephen Hawking in the 2004 film Hawking, read a heartfelt tribute. Here is an excerpt from his reading.
We are gathered here today to honor a man who not only changed the way we see the universe but also inspired countless people with his resilience, wit, and determination. Stephen was a great scientist and an extraordinary human being. His work on black holes and the nature of time has had a profound impact on the field of theoretical physics, and his legacy will continue to inspire future generations of scientists. But beyond his scientific achievements, Stephen showed us the power of the human spirit. Despite the challenges he faced, he lived a life full of passion and curiosity, never letting his illness define him. It is a privilege to celebrate his life and his contributions to our understanding of the universe. Thank you, Stephen, for showing us the true meaning of courage and for expanding our horizons in ways we never thought possible.
Cumberbatch's words encapsulate the profound impact Hawking had on both the scientific community and the world at large, celebrating his unwavering spirit and intellectual brilliance. The equation inscribed on Stephen Hawking's tombstone is a representation of Hawking radiation, a groundbreaking discovery that revolutionized our understanding of black holes. Hawking proposed that black holes are not completely black but can emit radiation due to quantum effects near the event horizon. This phenomenon, now known as Hawking radiation, suggests that black holes can lose mass and eventually evaporate over time. The equation is written as T equals the product of h bar, reduced Planck's constant, and the c, speed of light cubed, divided by 8 pi times g, the gravitational constant, m, the mass of the object, and k, the Boltzmann constant. In this equation, T is the temperature of the black hole, known as Hawking temperature. H bar is the reduced Planck's constant, fundamental in quantum mechanics, describing the quantization of energy levels. C is the speed of light, representing the ultimate speed limit of the universe. G is the gravitational constant, which measures the strength of gravity. M is the mass of the black hole. K is Boltzmann's constant, relating temperature to energy. This equation encapsulates the interplay between the fundamental constants of nature, illustrating how quantum mechanical processes affect black holes. Hawking radiation provides critical insights into the nature of black holes and the unification of quantum mechanics and general relativity. It demonstrates that black holes are not eternal; instead, they can shrink and ultimately vanish, releasing their energy back into the universe. This discovery opened new avenues in theoretical physics and remains a cornerstone of our understanding of the cosmos. In conclusion, Stephen Hawking's life and work have profoundly shaped our understanding of the universe. His groundbreaking theories on black holes and contributions to the theory of everything, coupled with his remarkable ability to popularize science, firmly establish him as one of the greatest scientists of our era. Hawking's resilience in overcoming adversity and his unwavering pursuit of knowledge continue to inspire us to push the boundaries of science and delve into the mysteries of existence. His legacy endures through his scientific achievements and his inspirational life story. As we probe deeper into the cosmos, his work remains a cornerstone for future discoveries. Hawking's triumph over significant physical challenges to make revolutionary scientific breakthroughs underscores the power of determination and intellect. Beyond the scientific community, he has sparked a universal admiration, motivating people of all backgrounds to pursue their passions and relentlessly question the world around them. Let me conclude with a quote that encapsulates my deep respect for him. My goal is simple. It is complete understanding of the universe, why it is as it is, and why it exists at all.